Hey guys, we are on the last new section of chapter 7, which is dilations and similarity in the coordinate plane. Coordinate plane being, your x and your y axis with some points and stuff. I'll try and do this quick and get you out of here in a relatively quick time. We've got this, I've got a couple here, and some answers and stuff on there. So I'll probably go through all the examples, but if you need anything or you need any more clarification, just ask in class. So a dilation is essentially a transformation that changes the size of something but not its shape. So it's a transformation that changes size but not shape. So to give you an example of what that looks like, I have a picture of Jason Mraz right here. I don't know if you don't know who that is. Sings that song, Lucky, and plenty of other songs that you might know. So if you take a look at the picture, the original picture here, and you put some coordinates on here, say that this was, I don't know, 3 inches tall, and we'll make it a 3 by 5 picture. So 503, sorry, let's change this and make that 5'3" to make sure that this is actually accurate. So you've got a couple coordinates, and what you can do in order to show what a dilation is I've got that picture in the background that you can see that's a little bit lighter. And a dilation would be if you took something like this size on the smaller picture and then you enlarged it to make it bigger. So I've got these two connected right now. I don't know if I can disconnect them. I don't think I can. So, but the idea being that you can take this small picture of Jason Mraz and you could stretch it out and make it a little bit bigger. And so say I just, I doubled all the coordinates. So I call this 10, 0. I call this point up here 10, 6. And then I call this point up here 0, 6. So what I've done is I've enlarged it twice the size that it used to be. And so you notice that it's not just twice the width or twice the height. It's actually, it's both of those at the same time. So when we talk about that, we also talk about a scale factor. So the scale factor for the small to the large would be you have to think about what you would multiply it by to get to the bigger one. So that's going to be a scale factor of 2. So my large one is, for example, we can look at one that was 10, and then that corresponds to the 5 on the smaller one, which would equal 2. The scale factor for large to small, and if I look at maybe a different one, so I do 3 to 6, and that equals 1/2. So that's a scale that you can multiply by the coordinates to show that they get bigger or smaller based on that. So if you take a look at this coordinate, I could take 2 and multiply it by 5, 0, and I should get 10, 0, which is that coordinate. So just shows you a little bit about what a dilation is. So we're going to use this in some examples and show how you can take these transformations and apply them to the coordinate plane, get some scales, and that's pretty much it. So I have some examples here showing dilations in the coordinate plane. And so I know that this one looks like a proof. We're going to do it kind of with some algebra and make it so it's not that hard. And yeah, so feel free to pause and try them out. Anyways, given this first one, we have these two triangles, and we want to find the coordinates of D and find the coordinates of, find the coordinates of D and then find the scale factor. So anyways, if I compare C and A, which I already know, so it looks like that goes from 4 down to 2 if I look at it from large to small, or if I look at it from small to large, it goes from 2 up to 4. So I need to go larger, and so I want to find the scale factor of, let's fix that, of the small one to the big one. So if I want the scale of the small to the large one, I'm going to take that 4, divide it by 2, and get 2. So I should take that coordinate, 3, 0, and I should multiply that by 2, and then I get 6, 0, which would be the coordinate of D. The scale factor would be 2. So again, you got to think when you're deciding whether the scale factor is 2 or the scale factor is 1/2. You got to decide, are you getting bigger or are you getting smaller? And yeah. The second question down here involves a little bit more. So it says that these two things are similar and prove why in the coordinate plane. So you have options. You could show side, 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 and you'd have to use the distance formula 6 times to show the sides are proportional. To show sides are proportional. I'm a little bit lazy and I don't want to do that, so I think what I'll do is I'll show that the lines are parallel. So I'm going to do angle, angle. So I'm going to show that BC is parallel to DE, which I can do because B is, what is that, -1, 4, and C is 3, 4. I realized that I labeled B incorrectly. It should be -1, 3. So anyways, I can show that slope is 1/4. It goes up 1/4. So the slope of BC is 1/4. And then DE, which is -3, 1. And then I can show E, which is 1, 2, 3, 4, 5, 3. So I got that. That also, the slope, it goes up 2 and over 8. So slope of DE goes up 2 and over 8, which is also 1/4. So these make the lines parallel. And then using that, I can also show that I have angles that are congruent. So now I've got these two angles congruent because they're corresponding. So angle ABC is congruent to angle ADE because they're corresponding. And then angle A is congruent to itself, which is reflexive. And that's how I can get angle-angle similarity. So similar by angle-angle similarity. So it's just one way that you can apply this to coordinates and show that they're similar. You could have done side, side, side. It's a lot more work. I don't feel like doing that. But you could do it. You know, sometimes you're not going to have that parallel line in there and you can't show that that's true. So that's just one way that you can do it. We'll get to the last few answers here. If I'm going too fast, again, just pause it and you should be all right. Okay, this one has me graph an image after a dilation with a scale factor of 2 and then verify. So if you remember, these little prime marks on this have to do with transformations. I know we did that way back in chapter 1, but that's how you note that something's a transformation. So if I do this quick, A is 2, 3. B is 0, 1. C is 3, 0. Now, if I multiply those all by 2, I'm actually going to take this and move it down over here for a second. So if I multiply them by 2, because the scale factor is 2, so that would be 4, 6, 6. This one would be still 0, 2, and this one would be 6, 0. So I'll do those in red to show. So I've got 1, 2, 3, 4, 5, 6, 0, which is C prime. I've got 0, 2, which is B prime. And then I've got 4, 6, 4, 2, 3, 4, 5, 6, which would have been A prime. So connecting those and showing the two triangles, it's not the neatest thing in the world, but it works. So you can see that one is twice as big as the other one. So it said graph the image and then verify that they're similar. So I did graph the image after that dilation. If I was going to verify that they're similar, this part here, that's where I can use either angle, angle, side, angle, side, or side, side, side. In this one, I would probably have to use side, side, side because it doesn't look like, I mean, I could show that they're parallel by using the slopes again, I think. But since there's not a common transversal, it would be a little bit harder to show that. So I think side, side, side would be the best option. To show you maybe one of those, I don't want to do them all out, but I could show you one if you wanted to see that. So let's just move these. to show, for example, actually, well, you could show, here, let's get rid of that. I could show what this side is. I know that this length here is 3 and this length is 1, so 1 squared plus 3 squared equals BC squared. So I should be able to say that 1 and 9 is BC squared, so BC is the square root of 10. I could then show that B prime, C prime is the same thing, so which starts, we're going to show this. So if I do that, I've got my length on the bottom here looks to be 6. So I've got 6 squared plus then my length on the y-axis, which would be 2. So 2 squared equals B prime C prime squared. That's 36 and 4, which is 40. So BC is equal to the square root of 40. So I would be able to say that B prime C prime over BC is equal to the square root of 40 over the square root of 10. Now that top one reduces. I can take a 4 out. So that's 2 square roots of 10 over the square root of 10. So it looks like my scale is going to be 2. So that's one way to verify that I've done it correctly. I could show it then for all the other sides, but for this example, I'm not going to do that. So, but if you were going to verify it, I at least did verify it with 1 by taking this and showing that, yes, they did come out to 2. On the next example over here, you can see, this is a little blurry. I'm given that those triangles are similar and I need to find the scale and the coordinates. This one's a pretty simple question. I'm just going to move it over a little bit so that I can see it a little better. So I'm given that P is negative 15, 0. I have M is negative 10, 0. And I have Q is negative 30, 0. 0, negative 30. So I can find out what the scale is by just dividing the larger number over here by negative 10. So if I do negative 15 over negative 10, I get 3 over 2. So it looks like my scale is 3 over 2. But I need to go from the large one to the small one. So I did large, small. If I want to go from the larger one to the smaller one, I'm going to have to flip that. So small over large would have been 2/3. I've just flipped that around to get 2/3. If I had multiplied negative 30 by 3 over 2, it would have gotten bigger. So now I'm going to take that coordinate, 0, negative 30. I'm going to multiply that by 2 over 3. So I end up with 0, negative 20. So that's what that coordinate is. And my scale factor is 2/3. So that matches up with my answer. Got those, and I've got those. All right, I've got one more example down here that I can show you. It says, which triangle with vertices D, E, and F is similar to ABC? You have options here. So you can get the coordinates and you can check the scales. This coordinate is, I've got, what is this, 1, 2. I've got this one, which is 1, 2, 3, 4, 5, 2. And I've got C, which is 3, negative 2. So I'm going to need something proportional. I could graph them all and look and see which one works. So, for example, if I graph A, D is 1, 2. Oops, I should probably do that in green. D is 1, 2. E is 3, 2. 1, 2, 3, 1, 2. And F is 2, 0. Which is here. That actually looks proportional. So I'm thinking it's going to be this one. I'll just check and make sure that these lines are parallel first. So if I check that, I can start at F if I got a slope of 2 over 1. So this slope is 2 over 1. If I check this line here, it goes up 1, 2, 3, 4, and over 2. So 4 over 2 is a slope of 2. So since the slopes match, then I know that, yes, that is going to be proportional. So for me, graphing it is the easiest way to check. You could have done that for all the other options, but that one is definitely going to be proportional. So anyways, if that was a little quick, you can go back and you can check some of them. You can always ask in class, but as promised, pretty short.